Hello everyone, welcome to my channel. I hope you like this video. My name is Essam Badakhshan. I'm from UPC, and in this presentation I want to talk about the behavior of a vegetated slope in terms of thermo-hydro-mechanical and some points regarding the simulation of a slope by considering all of these conditions. In this presentation, I want to talk about one short introduction, and then I will move to present some formulation about the model and also the most important part about verification of the model and using this extended model for two practical cases in terms of rainfall forces and thermal forces, and finally I will sum up with some conclusions. Generally, when it comes to vegetation, it is important to consider three important effects as a thermal behavior, because thermal condition can affect the instrumental behavior. In very high temperature condition, it will be close, and when the temperature reduces, it will be low. The hydraulic behavior, there is a statistical effect. When we have rainfall, some parts it will infiltrate in the soil, and some part will be evaporation or transpiration, and finally the rest will behave as a surface runoff. And the mechanical part, that is one important parameter for thermo-hydro-mechanical simulation of vegetated slopes. In a BBM model, we can consider three items as a deviatory stress, pre-consolidation pressure, and suction. And the experimental results show that BBM is effective in simulating the failure surface of vegetated soil as well as non-vegetated soil. But the main question is that how we can reach from a bare soil to vegetated soil. Firstly, let's have some summary about the basic formulations of the BBM. BBM is works with elasticity and plasticity. In elasticity, the deviatory and volumetric strain has related to temperature. Also, it is related to the suction. Here is the main item that we have considered for simulating the vegetation, is the pre-consolidation pressure in saturated condition for vegetated slope, as well as one parameter like lambda S is important for considering the effect of vegetation. For simulating vegetation, we focus on the behavior of the R, and for this behavior, it is necessary to consider the hardening. In a previous BBM model, the hardening was only related to the mechanical part, but when it comes to vegetation, it is important to relate the hardening behavior to the root behaviors. So the hardening is related to the parameter R with two items. First, MVEG, that is called to initial root mass, to the total mass of soil and root composite, and the parameter RPV, that is the root constitutive parameter that considers the effect of roots on the strain of the root soil composite. For the first part, the mechanical hardening, the equation is related to void ratio and plastic strain. But in terms of vegetation, we define two items to make a progressive hardening and softening for the behavior of the soil. So it has defined with three items as a RP initial, peak, and finally it will reach to residual condition as the strain in residual level. And you can see by increasing the parameter R, the failure surface will be reduced, and if we reduce the R, it will expand. So it can show how the vegetation can affect the failure surface. So by defining this parameter, we are reducing the parameter R, and in other words, it has an effect on the expanding the failure surface, and it means we have hardening. And when we reach to a strain at the peak stress of the vegetation, the softening will be a start. And here is the two failure surface that show how the vegetation that has shown with the green failure surface will affect the BBM. When we have a more concentration of the vegetation, also the failure surface will expand. And in terms of the critical state line for vegetated and non-vegetated slope, this is very similar, but the vegetated soil has a higher critical state line. For the model, it is possible to consider two soil water retention curve, first hysteresis soil water retention curve and dual porosity. Both of them is implemented in codified, and it is possible to use all of them. But for this research and this presentation, we have used dual porosity soil water retention curve and a bunch of parameters for this model. For considering the vegetation, it is important to consider 5 extra parameters as initial root reinforcement, peak, and residual reinforcement, and the strain related to the peak and residual condition, and finally the ratio of the vegetation inside the soil composite sample. Here is some validation to find the model is working well or not. Here is some experimental tests from Liu and et al. In 2011, and there are 3 layers of vegetation in this directional test. The size of sample is near to 80 millimeters with the diameter near to 20 millimeters, and it has tested in 3 different concentration of the vegetation, 2, 4, and 6 gram per each layer, and 1 without vegetation. Here is the animation of the behavior of the triaxial test and the comparison test, and there are a clear cluster that show the vegetation stress inside the sample. And if I want to compare these results with experimental test, there are a good confinement between experimental tests and numerical results, and the agreement between both results show the model is effective in simulating the vegetation. Another validation is about one large triaxial test with the height of 40 centimeter and a dual porosity soil water retention curve for vegetated as well as for non-vegetated. For this sample, we have tested in 4 different section level and different combining pressure. For verification of the parameters and calibration of the parameters, we used one bare test and one vegetated in 2,900 kilopascal section, and then we tested the result with the rest of sections. And here you can see the volumetric strain of the vegetated and non-vegetated sample. For vegetated sample, the vegetation has reduced the bulging of the sample, and also based on the comparison between experimental tests and numerical results, there are also good agreement between the results. And the last part of the validation is about the tensile test. It is a special device that has built in UPC for testing the tensile behavior of the roots, and it has tested in 3 conditions: first bare, and then in 2 different section level. For the bare sample, the behavior is similar to localized cracks, but when we have vegetation in a low section, the behavior is very ductile and a non-localized crack, but in high section also the behavior is very brittle, and we can see the localized crack. This result is very close to the experimental test, and it showed the agreement between numerical results and experimental test. Then we use this verified model for simulating the slope behavior in rainfall in this deformation. We have used 3 raining cycles, and as long as with one raining with a lower rate but a higher duration. In each raining cycles, we have a deformation, but when the rate of raining is higher than the previous one, the deformation has increased. And we try to find the position of the root layer to find how it has an effect on the deformation of the slopes, as well as the stability of the slopes. The results show that when we cover the surface of the slopes with a full layer of vegetation, the deformation has reduced near to 20%. But when we put the vegetation in some localized region, it has an effect on reducing the deformation, but the amount of reduction depends on the position of the vegetation. And here also it is clear the failure surface of the bed and vegetated in different rainfall ratio. And in terms of the effect of vegetation on the liquid saturation, here is 2 models that show one bed and another vegetated slope. When we have a thermal loading, for example, for a 50 centigrade, for the vegetated slope, we have a 20% reduction in saturation degree. But for rainfall cycles in the peak rainfall condition, for the vegetated slope, we have 8% reduction in saturation degree. These results show how vegetation has an effect on saturation degree and the limitation of the saturation in vegetated and unvegetated slopes. And the conclusion of these results and these simulations can be presented in 4 different items. Firstly, the main result is that the strain-dependent parameter that I used and I mentioned by R parameter can effectively simulate the progressive behavior of the vegetation in terms of mobilization or degradation. And also the slope results show that when we have vegetation, it means that we have a more drier surface, and also the vegetation can reduce displacement near 60 to 70% in comparison to unvegetated slopes. And when we have vegetation in comparison to non-vegetated slopes versus thermal loading, we have more extra desaturation. And finally, the optimal position of the vegetation depends on the condition. But when it is not possible to have a full cover of vegetation for the slopes, I think the best position is the bottom or middle to toe off the slopes to reach the maximum effect of the vegetation. Thank you for listening to my presentation, and I hope you like this video, and please say in comments about the details of this presentation, and if you would like to learn more about this simulation, please comment me. and follow me. Thank you guys. See you.